You ever just look up at the night sky and think, like, how did any of this even happen?
It is pretty mind-blowing, isn't it?
Yeah, and today we're diving into one of the biggest mysteries out there, the Planck Era.
Ah, yes, the Planck Era. It's like the ultimate origin story.
Right. It's this crazy short period.
They're talking 10 euroseconds, basically the blink of an eye on a cosmic scale.
A tiny blink, and yet it set the stage for, well, the entire universe.
Everything we see around us, even ourselves, can be traced back to those first fleeting moments.
Okay, so help me out here. The Planck Era. The sources describe it as this, like, pre-universe universe where even the laws of physics were different.
It's a time so extreme that our current understanding of physics kind of just falls apart. Meaning, imagine a universe so small, it's smaller than a single proton.
Okay, I'm already lost.
But here's the kicker. It's packed with more energy than we can even fathom.
See, that's what blows my mind. How can something so tiny hold that much energy?
It really stretches the limits of our imagination, right?
Mm-hmm.
But that incredible density is essential to understanding the Planck Era.
Go on.
Think about it. If all the energy of the universe was crammed into that tiny space, it means the very nature of energy itself had to be different.
Different how?
It had to be unimaginably concentrated far beyond anything we observe today.
So it wasn't just that things were, like, hot and dense. It's that the fundamental building blocks of reality were different.
Exactly. It's like comparing a single drop of water to an entire ocean. And that leads to one of the weirdest things about the Planck Era. Quantum mechanics takes center stage.
Quantum mechanics, isn't that the stuff of tiny particles and, like, probabilities and all that?
It is, but in the Planck Era, those quantum rules govern the entire universe.
Whoa, hold up. So we have to ditch our comfortable ideas about gravity and all that.
For a little while, yeah.
Yeah.
We have to dive into a world where uncertainty reigns.
Okay, now I'm really intrigued. But uncertainty on a universal scale? That's just that weird.
Think of it like this. Remember Schrodinger's cat?
The thought experiment where the cat is both alive and dead at the same time.
Yeah. Well, the early universe was like a giant cosmic cat. A swirling mix of possibilities, where even space-time itself was in constant flux.
So instead of definite planets and stars, there was just this, like, blurry soup of potential.
A soup of potential, exactly. And in that soup, the laws of physics as we know them simply didn't apply.
Meaning?
Things like gravity and electromagnetism hadn't separated out yet. They were all part of this one unified force.
Okay, back up a second. Unified force, what does that even mean?
It's like instead of four fundamental forces, gravity, electromagnetism, the strong and weak nuclear forces, there was just one superforce governing everything.
Like one rule book for the whole universe. But then it split up.
Precisely. As the universe expanded and cooled in those first fractions of a second, this superforce couldn't hold together.
So it fractured.
Yeah, and that's when things really started to get interesting.
This is where we get the universe we know and love.
In a nutshell, yes. The way those forces separated determined everything that followed.
Wait, so you're telling me that if things had broken differently, the universe would be totally different?
It's true. Imagine if gravity hadn't become its own force. There would be no stars, no planets, just this diffuse fog of particles.
So the fact that I'm sitting here on Earth talking to you, it all comes down to that split in the first moments of the universe. That's wild. But I'm still stuck on one thing. The Planck Era lasted for, what was it, 10 euroseconds?
A tiny sliver of time.
How can we even begin to understand something that happens so fast? It's like trying to study a single frame in a movie.
It's a huge challenge, but not impossible. And this is where the concept of Planck time comes in. Planck time is the smallest meaningful unit of time.
So 10 euroseconds, that's the smallest unit of time possible.
As far as we know, yes. Anything shorter just doesn't make sense in the realm of physics. It's like the tick of the cosmic clock, and during the Planck Era, the entire universe existed within a single tick.
So in that one tick, everything was decided. All the possibilities, all the potential, condensed into this infinitesimally small moment.
And that single tick set in motion the chain of events that led to the universe we see today, in all its complexity and wonder.
Okay, my brain is officially fried. We're talking about timescales and concepts that just defy human intuition.
It's true, the Planck Era pushes us to the very edge of what we can comprehend.
Yeah.
But that's what makes it so fascinating to study. It's like peering into the very heart of creation.
And to think, it all started with a bang and a whole lot of chaos.
A bang, some chaos, and a dash of quantum weirdness.
You've definitely got that right. I think we need to take a moment to let all of that sink in. Don't go anywhere, because when we come back, we're diving even deeper into the Planck era, exploring what it means for our understanding of reality itself.
It really makes you wonder, doesn't it? How something as chaotic as the Planck era could give rise to the order and structure we see today.
Yeah, it's like you look at the night sky and everything seems so organized.
Exactly. Galaxies, stars, planets, all following these predictable laws of physics.
But knowing that it all started from this, like, quantum frenzy, it's mind-blowing.
It challenges our assumptions about how things work, right? We tend to think of order and chaos as opposites.
Yeah, like oil and water.
But the Planck era suggests they might be more intertwined than we realize. Like, maybe you need that initial burst of chaos to create the potential for something new.
That's a really interesting way to look at it. So are you saying that, like, chaos is the seed of order?
Maybe. And, this idea of potential is key to understanding what happened after the Planck era. Remember we were talking about symmetry breaking? How that superforce fractured into the four fundamental forces?
Right, like the universe suddenly had a whole new set of rules to play with.
And it's all about how those forces interacted with each other and with matter that led to the universe we see today.
Okay, so walk me through it. How do we go from this formless soup of particles to stars, galaxies, planets, all that good stuff?
Well, let's take gravity, for example. Once it was on its own, gravity could start pulling matter together, clumping it into denser and denser regions.
So gravity was like the cosmic sculptor shaping the universe.
Exactly. And those clumps eventually became the seeds for stars and galaxies.
Okay, gravity, I get it. It pulls things together. What about the other forces, like electromagnetism?
Well, electromagnetism created light, for one thing. And it also governs how charged particles interact with each other. So it played a huge role in shaping the early universe.
Okay, I'm following you. Gravity brings stuff together. Electromagnetism does its electromagnetic thing. What about the strong and weak nuclear forces? Those always seemed a bit more, mysterious.
Ah, those are the forces that operate on a much smaller scale, inside the hearts of atoms. The strong force is what holds the nucleus of an atom together, binding protons and neutrons.
So without it, atoms would just, like, fly apart.
Exactly. It's incredibly strong, hence the name. And then you have the weak force, which is responsible for certain types of radioactive decay. It plays a crucial role in how elements are formed and transformed, especially inside stars.
So even though we don't see them directly, these forces are essential for, well, pretty much everything.
They're the unsung heroes of the universe, holding matter together, creating elements. It's all thanks to them. And the thing is, the specific way these forces separated, the exact moment and manner of that symmetry breaking, determined the kind of universe we live in.
Wait, so you're saying if things had gone down differently, the universe could be completely different? Like no stars, or maybe just a giant black hole?
Exactly. There are countless what-if scenarios that cosmologists explore. What if gravity had been a bit weaker? What if electromagnetism had been stronger? The possibilities are endless.
So our universe is just one outcome out of like a million. Kind of makes you feel special, doesn't it?
It does, and it makes you wonder, why did our universe turn out this way? Was it just random chance, or was there something more at play?
Yeah, like some cosmic architect designing things just so.
That's a question that delves into philosophy and maybe even theology. Some people believe that the universe was fine-tuned for life, that the fundamental constants were chosen to allow for our existence.
Okay, that's getting a bit too deep for me. But I do like the idea that our universe is, like, special. That it's not just one random outcome, but something more.
It's a thought-provoking idea, isn't it? And even if we don't have all the answers, it's questions like these that drive scientific inquiry and push us to explore the unknown.
Right, and it's not just about understanding the universe out there. It's also about understanding ourselves, our place in the grand scheme of things.
Exactly. Learning about the Planck era, about the origins of everything, it forces us to confront some pretty big questions.
Questions like, what is time? What is reality? Why are we here? All that fun stuff.
And even if we don't find definitive answers, the process of asking those questions, searching for answers, that's what enriches our understanding of the universe and of ourselves.
Well said. I feel like we've covered a lot of ground in this deep dive.
We have, but there's one aspect of the Planck era we haven't touched on yet, and it's a big one. Time.
Oh yeah, we left off on a bit of a cliffhanger there, didn't we? You were saying that the Planck era challenges our very understanding of what time ISS?
It does. We humans tend to think of time in a very linear way. Past, present, future, always moving forward. But the Planck era suggests that our everyday experience of time might be a very limited view.
Okay, now you've got my attention. So, how could time be different? Are we talking like time travel?
Not quite time travel, but perhaps something even more mind-blowing. Remember we talked about Planck time, that incredibly tiny unit of time, the smallest tick of the cosmic clock?
Yeah, 10 to the power of negative 43 seconds, right? Hard to even wrap my head around that.
Exactly. And some physicists believe that Planck time might be more than just a theoretical limit. It could actually be the fundamental grain size of time itself.
So instead of time flowing smoothly like a river, you're saying it could be more like a series of snapshots, like frames in a film.
That's one way to visualize it. Imagine each frame of that film representing a Planck time unit. In our everyday world, those frames would be so close together that we wouldn't even notice the gaps. But at the Planck scale, those individual moments might become significant.
Whoa, so are you saying that reality could be like a stop-motion film jumping from one Planck time to the next?
It's a fascinating idea to consider. And if time is granular like that, it has huge GE implications for how we understand everything. Cause and effect, the arrow of time, even the nature of reality itself.
Okay, this is getting seriously deep. So how does this all affect our attempts to understand the Planck era? If time itself was different back then, how can we apply our current theories and models?
That's the challenge, isn't it?
Yeah.
The Planck era forces us to confront the limits of our current knowledge. It's like trying to read a book written in a language we don't understand. We may have glimpsed a few letters, but we're far from deciphering the whole story.
So where do we even go from here? How do we start to make sense of this cosmic enigma?
It's going to take a combination of bold new theories, A&D ingenious experiments. On the theory side, physicists are exploring frameworks like string theory and loop quantum gravity. These are attempts to reconcile general relativity and quantum mechanics.
And those theories could give us a new way to look at time, a way that actually makes sense in the context of the Planck era.
That's the hope. By unifying our understanding of gravity and quantum mechanics, we might finally have the tools to probe those first moments of the universe and understand how time itself emerged.
Okay, that's the theory side. What about experiments? Are there any ways we can actually test these ideas about the nature of time?
It's incredibly difficult, but not impossible. Cosmologists are constantly searching for clues in the cosmic microwave background radiation, the afterglow of the Big Bang. By studying subtle patterns in this radiation, we might find evidence to support or refute our theories about the very early universe.
So it's like cosmic detective work, looking for clues from the universe's baby pictures.
Exactly. And who knows what other ways we might find to probe the Planck era as our technology advances. Maybe one day we'll even be able to recreate conditions similar to those first moments in a lab setting.
Whoa, recreate the Big Bang. Now that would be something.
It would be revolutionary. But even if we never achieve that, the journey of exploration is what matters. The Planck era reminds us that there's still so much we don't know, so much left to discover. It's an invitation to keep questioning, keep pushing the boundaries of our understanding.
Well said. When we started this deep dive, I never thought we'd end up talking about the nature of time itself.
It's amazing where these explorations can lead us, isn't it? The Planck era might be shrouded in mystery, but it's a mystery full of potential.
It reminds us that the universe is far stranger and more wonderful than we can possibly imagine.
And that even from chaos, incredible things can emerge.
Well, I think that's a perfect place to leave it for today. Thanks for taking us on this incredible journey.
It's been my pleasure. Remember, keep looking up at the stars and never stop asking questions.
And to all our listeners, we hope this deep dive has left you with a sense of awe for the vastness and mystery of the universe. Until next time, keep exploring.